Okay, so I should ready to get started. So I'm going to spend, I kind of assume most of you had no idea what factorization homology is, so I shall explain this first word to you in this talk. So I apologize to anyone who, well, does know what I'm talking about. So basically, the idea is a factorization homology. What you do is it's a way of constructing invariants of manifolds. So what you do is you associate some object in some kind of infinity category to a disk, and then you sort of integrate this, what you assign to the disk, across the entire manifold to give you a kind of invariant of the entire manifold. And so you denote it. So you have a surface, say, we will be working with surfaces, sigma, and in this talk, what we'll be assigning to a disk is rep QG, which are the integrable representations of G, where G is some Lie group. And this is the integral representations of the quantum group associated to G. Okay, so from this generalized abstract nonsense you cook up, you can extract something called the algebra, well, I call it the algebra of invariance. Which is A for algebra. Oh, yes, script A. Okay, and this algebra of invariance is interesting for, well, a few reasons, but the main reason is it's a quantization of the character variety. So the character variety as is the same one as on Monday, and a quantization in that you quantize a Tier-Bott Poisson bracket on the character variety. And that is a result of Bensley and that reference is also a good reference for the first about half of the talk. So those are the names. Okay. So the point is, on Monday, we already had a quantization that was proposed of the character variety in the case where G was SL2, which was the Kaufmann bracket skein algebra. So the question is this the same quantization? I.e., is script A, in fact, just isomorphic to the Kaufmann bracket skein algebra of the surface? Or do we get something? And the answer is hopefully yes. Okay? So in this talk, I will consider the two examples. In the example where you have the punctured torus, so genus 1 puncture, and the example where you have a sphere with 4 punctures. And in these cases, by the end of the talk, I will write down some algebras of this which show it is in fact isomorphic to this. Because at least for these surfaces, you actually have quite explicit presentations for this stuff. But this result would actually be a corollary of a slightly more general result, which is actually what I'm sort of working on at the moment, which is so there's an equivalence of categories between the representation, the factorization homology of rep 2G. There's some slight generalizations. You need kind of rigid braided tensor product stuff, so you could stick a few other things in there, but that's really the example I'm thinking about. And the co-completion, well, I mean just by co-completion, just stick in all of the co-limits. Of skein with respect to the same G of the surface. Okay, so that's basically, so this is essentially, this is a corollary. If this is true, this is automatic, this implies that this is in fact true for all surfaces and all the groups G. So this is essentially a test of this conjecture, if you'd like to think of it that way. Any questions? In which case, I suppose I should get on with the actual talk and stop. Yeah. What? Yeah, free co-completion, so yeah.
That was my question, but do you mean
okay.
co-completion?
Yeah, so it's just the free co-completion, just stick in all of the co-limits, basically. Yeah. What? So I mean by co-completion is you need to formally stick in all of the co-limits of the scaling category because it's not really closed on them. And if you stick all of those in, it makes a much larger thing, which is the factorization homology, because in general, this is a lot larger than this. Yeah.
So the factorization homology is an abelian category?
What?
Are you saying that the factorization homology is an abelian category?
Not quite. It lives in, well, it lives in Rex, which is not quite, but sort of getting, that's sort of the idea, but there's a few technical conditions because you want a tensor product and you use the Cayley-Delane tensor product, and for abelian category, AB is not closed under this operation, so you don't really want to use this. And so you put this representation in a slightly different category for basically technical reasons. Okay, so...
Even in the simple example,
what?
so in the example, so even in a simple one, like you always need this co-completion here. It's never...
Yeah, basically what I do in this is show this is true. So the skein, because this is, oh, that's not right, sorry. The skein, that's probably why it's getting a bit confusing. Skein category. Okay, so the skein category is basically like the skein algebra, apart from if you have a surface, you can start and end your links at any point in your surface, so at intervals, and you also have morphisms. So the skein category is larger than the skein algebra. And so I haven't computed what the skein category is for these surfaces, so I can't actually show it's directly so. But yeah, apart from this thing would be massive because all of the isotopies are relative to the endpoints. So you would end up with, it's quite a big thing. Yeah. Okay, so I'm going to start off with defining my factorization homology, and then I will later define the algebra of invariants. Okay, so what I need, firstly, is so everything here is living in infinity one categories, so I need an infinity one category made of manifolds. So I define a category of framed n-manifolds. You can do factorization homology with not framed things. You can play with oriented things, things with actions of groups, and there's a whole small zoo, but framed will do. Is a symmetric monoidal infinity one category. And the monoidal product is just going to be disjoint union of manifolds. Okay, and its objects are smooth, framed n-manifolds. Its morphisms are smoothed, framed embeddings between framed manifolds. The two morphisms are isotopies between the embeddings. And the three morphisms are homotopies between these isotopies and so on, really. So that all constructs you an infinity one category because all of this stuff is invertible. Okay, and now we have as a full, so disk, again in R, and framed is the full of disjoint unions of Rn. So basically, disk is some collection of disks, or balls in general in a higher dimension, and the embeddings of disks into other disks. So for example, the embedding of, say, this disk into that disk, for example. That will do. Okay, and I also need just a random category, C, which is a symmetric monoidal infinity one category. Okay, I should clean the boards. So any questions? Did you say?
It would be better to cut another one.
Oh, yes, sorry. I guess it's probably too late now. our categories, if you remember them. Left can extension. I mean, if it exists. Of the embedding. So what you do is you take the disk. What you need is F. I forgot this. F is a, well, what you expect it to be, a symmetric monoidal functor from this category into our infinity n category. And we call F a En algebra. Now, this definition as a symmetric monoidal functor between disk and some other category is not the standard definition of a En algebra, which is a little disk operad, but it's equivalent, which if you look at, say Francis, they have this. And basically in factorization homology, this is the definition you use. Anyway, so what you do is you extend your map from the disks and we call the result the factorization homology. Okay, so where with the coefficients. And this squiggly E is just F applied to a single disk. Because disk is just a disjoint union of, well, disks, this specifies what what F is on objects, and by an abusive notation, we usually just refer to this thing as the En algebra. Or at least, I probably end up doing this far too much. Okay. Okay, yeah, so from now on, we're just going to assume n is equal to 2, and so we're working with surfaces. Okay, so the next thing is to choose this category C. Yeah.
Can it also in some cases be defined as an end or co-end, or by notation?
I mean, a lot from the left can extension, I'm sorry, my left has no T, but anyway. It's often equivalent, like a lot of the time, in all the cases I'm dealing with, this left can extension is just a co-limit. And so I'm really treating it as a co-limit, but this is the, I guess, the sort of general definition. So yeah, a lot of the time it's equivalent because all of this stuff in category theory is, you know, choose your language really to under certain technical conditions.
It's co-end even though the sigma is downstairs.
I'm not sure. I've never really thought of it as a co-end. I've thought of it as a co-limit before, but never as a co-end, so I haven't actually thought whether it actually is one or not. Oh, yes, you're right, I think. So then, yeah. Okay, so I'm going to choose a category. I mean, there's a few categories you could choose. I mean, some people like to soup up vector spaces a lot, but I'm going to choose Rex, which stands for right exact. And Rex is a 2-1 category. So what we do is we consider it as an infinity n category just by truncating the mapping spaces, because 2-1 category is quite high enough a category for me. Okay, of essentially small. Okay, this is basically just a technical condition, so you don't end up with too much set theory, having to do too much set theory when you're meant to be doing, well, algebra. And this is finitely co-complete. What that means is it's complete under finite co-limit. So finite co-limit means that the diagram shape is a finite category. So, and k-linear categories. And, well, that means it's enriched over k modules or k vector spaces. And in this talk, k is just the, well, C. Okay, so I need to describe the, I need to define the homomorphisms, which are right exact functors. Hence, well, rets. And and natural isomorphisms as two morphisms. Okay, so the important thing to note about this particular choice of Rex is it satisfies two categories. Left can extension. Always exists, which, to be honest with you, is a relief to me. Probably to, you know, I'm not the only one that's slightly relieving. As one probably doesn't want to start computing something to realize that the thing they're doing isn't really well defined. Okay, it contains these integral representations, which is good. And we can define the Kelly-Delane tensor product. In particular, if you take the tensor product of two Rex categories, you always get a Rex category, which is why you don't choose abelian categories, because if you do that, it is not true. And I'm not going to define the Cayley-Delane tensor product here because it's not really relevant to this talk. And the only thing is, we can also do one better and define the relative Cayley-Delane tensor product, which is only really useful for, well, this is quite important because it allows you to define an excision property. So this, well,
Tensor product, what is often just called the Delane product?
yes, and I think it's often, yeah, it's often called the Delane one, yeah. So, yeah. I'm trying to think if there's any particular differences. Kelly may have slightly extended it. Not sure. Okay. And so, by construction, this factorization homology has three nice things. Well, more than three, but...
What did the group G appear into the picture?
No, Greek G?
Where did it appear into the picture?
Okay, so G is our Lie group. So...
But to have, like, in which part of the construction does it show up?
Well, it shows up here. Literally, the Rex contains this category, which is the integral representations of the... well, it's not so much in... Yeah, it's just one of the objects of it. So, and in particular, this is the object that we wish to assign to the disk. Of the codomain.
It's an object of the codomain.
Yeah, so it's our object of squiggly C. And so that's where it turns up there. And this is the object. So if this EN algebra has to assign things to disks, and that's what I'm going to assign to a disk, so this particular category. And this is just a Lie group, and these are integral representations of the quantum group, which is what the little q is. Here is denoting it's the quantum group instead. So that makes sense? Okay, so nice things. Okay, so it's an invariant. Of surfaces, which is basically pretty much just by construction, or by, you know, that's not really a tricky thing, but usually you have to prove things to prove your invariants are invariants. So this time we automatically have an invariant, and the hard thing is working out how to calculate the thing. Okay, and the second nice thing is it satisfies an excision property. Which means if I take some surface, which is the collar gluing of two surfaces, so this would be then the factorization homology of the glued surfaces for any EU you'd like to choose is equivalent just as a category to the factorization homology of the first one. The second one relative to the part they share, which is why, as I said, you need to define a relative tensor product for this statement to make sense. But if it does make sense, then you kind of have it, which makes no kind of sense, because if you think about it, it's just local. Factorization homology is just defined on little disks, so you would expect it to. And okay, so if you take a punctured surface, this is always a module category where you consider the action, just so if you have some kind of puncture, you can consider actions by just embedding disks and things like that. But often it is just the category of modules of an algebra. And in particular, in the case we're considering, that is the case. And so I am going to write a theorem, which again is down to B, Woher, and Jordan. So same people as I said earlier. And it just basically says, let sigma be a punctured surface and then the factorization homology of rep QG is isomorphic to some algebra, a sigma modules, and the modules are internal to, well, modules of rep QG. Where is determined from a gluing pattern. And so instead of saying the general case, I'm just going to go through the two examples I said I would do earlier, the punctured torus and the four-punctured sphere. Is there any questions?
Yeah, can you say again what you mean by so A sigma mod, so FQG is you mean it's modular?
What?
So A sigma is an algebra object in RepQG, or what is?
Yeah, so RepQG is, well, a load of representations, and this is one of them, I think. Yeah. So it's internal to this larger category of representations, I think. Yeah. Okay, so I'm going to do this on these two examples. Okay, so the first example is, I guess, the four-punctured sphere. Now, four-puncture sphere has essentially 4 punctures. So it looks like this, so just flatten it out onto the plane. And so then we can see that this thing has 3 handles, which is what the gluing pattern is. It just is a rule for gluing handles onto a disk, which gives you something homomorphic to your surface. Okay, so as it's got 3 handles, A sigma has 3 cappies of squiggly O, where squiggly O is the reflection equation algebra of UQG. Okay, so yeah, and these handles are linked, which means that between the copies, we have a map which permutes the copies. So the crossing morphism between, say, is essentially, this lives in, I guess, V tensor V, where V is the standard representation of this quantum group. And so you braid it. Like this. Okay, and right. This is where I should probably do that way. And okay. Actually, no, I should write something on this. What did you say?
Did you say that the reflection algebra is the same, the reflection equation algebra is the same as V star tensor?
So just the reflection equation algebra of this quantum group.
What does that mean?
Okay, what it means is, okay, I have some generators and relations of this algebra. So I've said what this, so this is 0, 4. Okay, so 0, 4. The reflection equation algebra is something with 4 generators and 2 relations. The first one is this, which, if you can see it, is basically just that the determinant is 1, which, as you're working in the quantum group, oh yeah, sorry. I should point out at this point, I'm working in SL2. So this is the determinant relation, and this is called the reflection equation. So this thing here, which is in tensor notation. So basically, I mean, is an algebra with 4 generators satisfying the reflection equation, which is why it's called the reflection equation algebra. Okay? And so the overall generators of this thing is we had, yeah, sorry, I should probably do. What? UQ of G. So yeah, for UQ of G, the reflection equation is defined by having 4, well, yeah, so U has generators, so 4 generators. and relations one and two, where 1 and 2 are these, with just x being, that's not right, that should have an x. So yeah.
Sorry, so is the reflection, so the reflection equation algebra is an algebra object and then ref huge.
Well,
Is it an algebra or an algebra object?
it's just an algebra.
But it's also a module of
No, because you're considering modules of the algebra.
But A epsilon, or whatever, A sigma,
Yeah.
is an algebra object and rep QG.
No, the modules of it are. So yes, it is an algebra object of this, and it's constructed of 3 copies, tensor product of this other algebra.
But O itself is not.
Yeah.
Sorry, I'm a little lost. So you're saying that A sigma is a representation of UQSL2 as well as being an algebra?
No, what we're doing is we're considering representations of this algebra, and these. So yes, it's the algebra object. Sorry. Yeah.
Can I ask, kind of, if you would just have one handle there instead of 3 handles,
Yeah.
would the algebra object A sigma then just be the coed over V star tensor
Of what?
V? Is it just the algebra object coed over V star tensor V? Do you know that?
Okay, so if it had a single handle, the thing would literally just be the reflection equation algebra. And so the reflection equation algebra is just an algebra with 4 generators and 2 relations, which are, well, the determinant is 1, and it satisfies this second relation called, well, the reflection equation, which is where the name comes from. And because we have 3 copies, we have, 3 copies, we'll have 3 sets of relations, and which both so each of these are reflection equations, and we also have a final, which is just the crossing relation, which is essentially the tensor form of that diagram I drew up there. Of an R matrix? No, it, okay, yeah, sorry. This is probably what I should point out. These R's here are R matrices. So yeah, this R is, these are just entries of R matrices. So technically, when I choose the reflection equation algebra of the quantum group, I should choose an R matrix, and I've chosen basically the standard one for this talk, which is this, the standard R matrix.
Is there any direct relations of the O and the quantum code with the algebra quantum code, the quantized code with algebra of SL2?
I'm not sure. No, I'm not sure.
because the skin algebra of that sigma 0.4 can be presented as the co-graded tensor product of 3 copies of that algebra.
In which case, probably yes. Yeah. Obviously, this O.
So the dependence SL2, so the 2 I see in the R matrix. Is this the R matrix?
Yeah, so this is the R matrix. So this is an R matrix for SL2 here. And from this L, and this is where we get all our relations from. So for example, when I braid up there, when you're braiding using the R matrix or, some kind of inverse R matrix and stuff like that. So yes, I kind of slightly messed up because, well, this is actually the algebra. It has 3 sets, and this is the braid relation, but this is, well, this is the quantum. I should probably just clean the board. Any more questions? Yeah, I should probably say that this little O is actually the pointing, in general, the pointing of the factorization homology. So it's the it's essentially mapping, it's related to mapping the empty manifold into your...
Can I ask what I think was Matt's question?
Yep.
And I don't know the answer.
Okay.
So down there on the bottom right, it looks like A sigma is an ordinary algebra over a ring. Give generators and
yeah.
But upstairs it says it's an algebra object in rep G.
Yeah.
G. So let's go together.
Let's see. Well, no, it's not. Okay, firstly, yeah, the algebra, it's the modules of the algebra that live in the representations, because otherwise it doesn't really make any sense, because rep is a set of it's a collection of representations. So you have to take representations of the algebra.
But the algebra itself is an object of rep QG.
No. It's modules are.
How does it act on modules then?
No, it's the modules of the algebra. So you consider the representations of, I think you consider the representations of the algebra. What? I don't know. Not sure. What? Yeah, I suspect it does. It's just I've never really considered. I mean, yeah, if I have. Sorry, at this point I should probably say is I never really worry too much about what A sigma is too abstractly, because I mostly just compute it. And so I often occasionally just sort of, because I've never actually really needed to use the theory of, these things, which I should probably keep that out. But yeah, I should probably just say that for my other example, which is you also have a handle thing with two handles, but they're now linked, which is why here the crossing relation is different from here. So yes, you basically, the number of handles determine the number of copies of the reflection equation algebra, and how the handles interact with each other determines the crossing relation. And yeah, and the other thing to note about this algebra is it's rather large, or both of them are. This one has 8 generators, and that one has 12, and it has a whole load of relations, so yeah. But I'm not gonna, well, as I said, I'd talk about the reflection equation algebra. I should probably do so before, further ado. So, if I have, I use script sigma.
Before you go on, could you show us maybe where the gluing pattern comes in? So here the two one-handles cross, and in the other case, the 3 one-handles don't cross.
Yeah.
Can you find us to the algebra relations?
Okay, so the algebra relations, if there isn't a second cover. So this algebra relation here is the one associated to the 4-function sphere. And so this is the crossing relation, which, if you look at this, this is pretty much just how you braid lots of copies of your thing together. And so this is this relation for the unlinked case, where for the linked case, you get this relation. So these two are not the same, not that you probably can see that, because, you know, but they are slightly different. And in particular, this one comes from considering a braiding like this. So it's a slightly modified braiding. All right. Yeah. And so, yeah, that, apart from the number of handles, is the only difference between those two algebras. So my algebra invariance is the internal endomorphism algebra of A sigma, all the parts of it which are invariant under the action of the group. So that's just by definition. And as I said before, this is gives a quantization of the character variety of the surface. Okay, so I should probably, and now I'm just going to put a big black box and say, this is now actually got to the bit that I actually did. This is all just background stuff that is required. And I'm actually just going to talk about what these are for some of these examples. Okay, so I'm now going to consider, I'm considering just the algebra object, so not the algebra invariance. And so this has generators. Some A's and some B's. Okay? And so we have quantum traces. I think I used Q minus 1. Okay, so A here just means, well, this algebra, this matrix. Okay, so these traces are invariant under this action. Okay, as actually are the traces of any power of A and any power of B. Okay, so these all give you invariants, so they should all be in this algebra. In the invariant, yeah. Okay, so we use, however, we can use the quantum Cayley-Hamilton equation, which is, yeah, basically the quantum Cayley-Hamilton equation as of some point in the 19th century, maybe, with Q's stuck in. And this quantum Cayley-Hamilton equation allows us to basically reduce the powers. And so write this as linear combinations of things with no squares in. So in particular, the traces are generated by just the quantum trace of A, the quantum trace of B, and the quantum trace of C. So we know that some of this this algebra invariance is made of just these three traces. Did I click this board? Yes, I did. C, oh, have I literally just? That's stupid. Right. When I don't take leave of my senses, this should actually be AB. Okay, and so my result basically now is Well, actually, we only have traces. And furthermore, so, I mean, you could think there might theoretically be other invariants which aren't traces of these matrices, but there aren't any. And also, we have actual relations between them all. So the proposition, basically, which is in, well, my preprint, is that this has a presentation with generators so just so I don't have to write out traces everywhere, I have and relations and three relations. And if you squint at this relation and know too much scaling theory, you will notice that these are actually isomorphic to just, so this is isomorphic. So the corollary of this. So where, if you remember from Monday, I think, where they described the presentation of this, so this gain has generators, let's call them x1, x2, x3, which refer to, okay, so if this is your torus, they refer to this, the other meridian, and also this. I think, if my conventions are right. Yeah. Okay. And relations just well, this is just the quantum Lie bracket, and so yeah, so this isomorphism is just look at it, maybe change some of the scale some of the generators by a power of q. And there is a second one, which is the other example. So, which is the other case, I mean, which is actually much more tricky to do in practice, which is the four-punctured sphere. Has generators. So now we have A's, B's, and C's, which is why I wrote C by accident. So we have, so this should be S, T, and so these are central elements, and AB, AC, BC, which is G, and relations 5 to 8, aka these relations here. Okay, So again, these are relations for swapping F's and E's, G's and E's, U's, and this slightly complicated cubic relation at the end. And again, this is isomorphic to, I should probably finish, to the skein algebra of the same surface. And the skein algebra of the surface, so S goes through round one of the holes, T goes round, U goes round the third, and then V goes round, I guess, the outside, and these other ones are the ones that go round two punctures. And so, yeah, so basically that essentially concludes my talk, as I proved what I said I would do. Well, I haven't proven, but I've at least stated what I said I would do at the beginning of the results, which is stated at the beginning of the talk. Any questions?
I still haven't understood what these generators and relations are. So you have an algebra object in some rigid braided category,
Yep.
graph QG, and then you give a presentation of such algebras in terms of relations and generators.
Yeah.
What does that mean?
I mean, it's just literally just a formal presentation. So this algebra is isomorphic to an algebra with these.
Generators are scalars, right? From the point of view of the tensor category. So what is the notion of generators in relation to an algebra object in such a tensor category?
I mean, in this case, it's just that it's isomorphic to an algebra with such generators and relations. So, I mean, any algebra has a presentation in a kind of formal manner. So, that.
How do you record the fact that it's an object in graph QG and it has an algebra structure in that factory?
Not sure. I don't think I do, but I'm not quite sure if I need to or not. I'd have to think about it.
If I can say, it looks like, I mean, this category is that Fourier functions are down to these vector spaces. No, Fourier functions are down to vector spaces, so you can present them in vector spaces.
But you would need an intertwiner from this representation, tensor the representation to itself.
Then the intertwiner is a linear map that happens to commute with the S section.
Okay. You know what you get?
No, I mean, that's what you, like, here Q is generic, right? So you have a,
Yeah.
you have a function
Yeah.
down to vector spaces. And every SL2 intertwiner is in particular a linear map that is commutes. I don't know, I guess I'm not speaking from a point of view of like knowing, I'm just saying.
I mean,
If you present everything in kind of vector spaces and then.
So then it's a strong statement that it lifts the tensor category.
I mean, I think probably if the statement's anywhere, as I said, this definition, like this example, this theorem is the theorem in this paper here. So probably if there's actually details, it's probably in there, which is called integrating quantum groups over surfaces. So that's where they do all of the framework to develop, I guess, this theorem here. And so probably that's the best way to place. I mean, I think, where they kind of go through all of the, what this stuff is a bit. Makes sense. Any other questions?
So do you have an idea how you could compute for an arbitrary surface, or is there give you again surface?
I mean, in practice, I wouldn't want to, because the method I used for this is actually quite concrete. What I did is I essentially just cooked up these algebras, and then I proved that they were isomorphism by calculating Hilbert series and then playing around with filtrations and stuff, which is really just not a generalizable method to anything with two linear generators and relations, because, which I mean, it's the, so for this thing. So if you're calculating the factorization homology, you have a general method. It's basically this. You just count number of handles, whatever, that generates your algebra properly. But for this invariant algebra, it's the method of actually calculating it seems a little hands-on at the moment. And so I'd like to look at, I mean, obviously, if it's isomorphic to Skane stuff, you could automatically use any results from, like, if you know the Skane algebra, you'd automatically know this. But I guess the interesting thing would be going the other way around, and I haven't really, you definitely need to cook up a bit more in terms of being able to calculate things in practice to be able to deal with a general surface.
So I'd be really curious to how this O compares to the time associated to the Weigron. Because that's the one you associate this to one.
Yeah, there's a lot of handles around this area because, I mean, in Skane algebras, if you're trying to construct the generators of a generic Kaufman Skane algebra of a surface, you then, well, you can have at least, if you consider these handle decompositions and then you consider all the different kind of loops, which are like, which you kind of think, like the ones that go around one loop, one that goes around two, then you construct generators. So yes, this handle decomposition stuff does actually turn up quite a fair amount in Skane theory, and it should somehow, well, it morally should kind of match up, but I'm not quite sure on the matching. Yeah?
So how do you